Hello and welcome back. In this video, we're going to look at waves in general with little to no electromagnetics. So this is the mathematical description of waves. Now, in general, a wave will satisfy, we're still going to use E though for the wave. The wave will satisfy the following equation. And this is just in one dimension. So you'll see the dimension I'm using here is z, but this could equivalently be x or y. And then we also have the variable t. So really we have a spatial dimension and then of course the time dimension. So we would call this one-dimensional because of one space. So this is what's called the wave equation. And any wave has to satisfy this equation. It's really kind of the definition of the wave, at least the mathematical definition of the wave. And u here is a constant, and u is the wave speed. And some texts, some references will call this the wave velocity, and I don't like velocity because u is a scalar, not a vector. And so you can think about what you remember from physics about the difference between speed and velocity, and speed was the scalar. And so I'm going to call this the wave speed. So you might ask, well, what kind of things E satisfy this equation? Well, I'm going to write E plus is any function of z minus u times t. That will satisfy it. Anything with where z and t appear like this will satisfy this equation. And this is a wave that's moving to the right. Think about in algebra when you have minus something in time, when time is positive, then that shifts the graph to the right. So this is a wave that would be moving to the right, hence the plus sign. Also, any function g of z plus u of t. So this is a wave that's moving to the left. And again, it's any function. So as long as z and t appear together like this, z plus ut, any function of z plus ut will satisfy that equation. And the neat thing about the wave equation, you know that waves interfere and they obey superposition. So if you have two waves that solve that equation, then the superposition or the addition of those waves will also satisfy that equation. Now, so let me just give you some examples of what these functions could be. Remember, they could be anything as long as z minus ut or z plus ut, they occur like that, they occur together. So for example, sine of k times z plus or minus u of t, u times t. That would satisfy the wave equation. Cosine of k times z plus or minus u times t would satisfy the wave equation. And just another example, e to the jk times z plus or minus ut will satisfy that equation. Actually, there are an infinite number of possibilities that will satisfy that equation. They don't all have to be harmonic. These are the harmonic wave functions, but they can just be, for example, the simplest function is just z plus or minus u of t. This is not harmonic, but it still will satisfy the wave equation. Here, the wave grows with space linearly, z, and changes linearly with time as well. Now, I'm not going to prove all of these things satisfy the wave equation, but I'll prove just one. So we'll just prove that the sine satisfies the wave equation. So how do we do that? Well, we just plug it in. So we're saying that this is E. So we just plug that into the wave equation. Well, I have a second derivative in time. So let me take first derivative first. So this would be the first derivative of k, sine of k plus or minus, let's see, ut, like that. Okay, and so the derivative of this thing versus time, well, the plus or minus u has to come in front along with the k, and then the sine changes to cosine. So I have plus or minus k u, right, times the cosine of k z plus or minus ut, like that. That's the first derivative with respect to time. Now, when I take the second derivative with respect to time, right, the second derivative of this thing, then I'll have another plus or minus uk coming out in front. So now the plus and the minus don't matter, right? Because if it was minus the first time, it's minus again, that makes a plus. And if it's plus the first time, it's plus again, that makes a plus. But then when you take the derivative of cosine, that makes a minus sign. So now when you take the second derivative of this thing, there's no doubt about it, this is a minus k squared, because the k comes out in front again, and u squared, right, because the u comes out in front again. And then this becomes again sine k z plus or minus ut, like that. Okay, now, so that's our first term in the wave equation. Now we have a second derivative in z, and I'm not going to show you the steps. I trust that you can take a derivative twice. Okay, so if we did take the derivative twice with respect to z this time, what do we get? We get minus k squared from the chain rule, and then the sine k z plus or minus ut, like that. So the question now is, remember, does the sine satisfy this equation, the wave equation? So we plug in now and see if it does. So this was the second derivative with respect to time, so I would plug that in up here. And then this here was the second derivative with respect to space, so I would plug that in here, and then I would multiply it by minus u squared, which would make plus u squared k squared. And when I add it to this, which is minus k squared u squared, I get 0. So yes, it does work out. It does satisfy the wave equation. And the other ones do too, and I'll just let you verify that on your own time. So like I said, the solutions need not be harmonic, okay? But if we do assume a harmonic solution, then say E is our wave, we can write E, remember, as a phasor, ES, and factor out the time dependence like this, E to the j omega t. Now, if we take a second derivative with respect to time, so if we assume a time harmonic wave, and then take the second derivative with respect to time, what do we have there? Well, remember that differentiating with respect to time is like multiplying by j omega in phasor domain. So when we take two derivatives in time, that's like multiplying by j omega twice. And of course, j times j is minus 1. So we would have minus, and then omega squared es e to the j omega t. Right? So if our wave is time harmonic, then its second derivative with respect to time is given by this thing here. And then how about the spatial derivative? So if we took the second derivative of E with respect to Z, well, we're not assuming anything about, so the spatial dependence is in the phasor ES, and we're not assuming anything about ES. So we really can't do much at all here. We just say, well, we have e to the j omega t times the second derivative with respect to E, like that, without ES, without making any assumptions. Okay, so now I can plug this into the wave equation. And the real parts, that real operation cancels. And then, you can divide by the real part if you want to think of it like that. And then e to the j omega t is in both terms there, and so that drops out as well. So when I plug those in to the wave equation, again for a time harmonic solution, then we would have negative omega squared es, that's from this part here, the time dependence, or the time derivative, and then minus u squared from the wave equation, then times that second derivative on es with respect to space, dz, equals 0. Right? That's what the wave equation tells us. And now I can rewrite this a little bit, and I'm going to introduce a new wave parameter. So I'm just multiplying by a -1 and then rearranging things, and I'm going to call beta squared actually. I'm going to introduce beta squared. And so what we're saying here is that beta is this new parameter. It's omega divided by u, like that. So now we know then that the solutions to this would be some constant a, e to the j omega t minus beta z, and then we would, so we can call that E plus, and then we would have E minus, and so we would have some constant B times E to the J omega T plus beta Z. And you might ask, well, why is that a solution? Why are those two things solutions to this? And the reason is, again, you can plug these into this equation and verify that it's true. But the reason is we have something ES plus its second derivative gives you 0. So that if we put ES on the other side, it's like saying ES is equal to its second derivative. So what function do you know that when you take its second derivative, you get back the original function, and that is actually a complex exponential. And so again, you can verify that these two things solve that equation by putting them into the equation. And then also then, not only do they solve the equation, but then the superposition of those two solve the equation as well, right? The addition of those two. And here we're saying that, again, capital A and B are real constants. Now, remember that the relationship between complex exponentials and sinusoids are regarding Euler's formula, where we can take the imaginary parts and the real parts. So for example, the imaginary part of A times e to the j omega t minus beta z, what is that? Pause the video if you'd like. That is A times sine of omega t minus beta z. So don't forget that. So we're using phasors as a shorthand to represent sines and cosines. Okay, so now let's get into some terminology to describe our waves. A is what's called the amplitude, and it has the same units of our field, E. So for example, if our field E is electric field, volts per meter or newtons per coulomb, then A is in volts per meter or newtons per coulomb. If E was like, if our wave was like sound pressure, then A would have units of sound pressure. Okay, omega t, so this was the amplitude, omega t minus beta z is what we call the phase. So that's the thing that you plug into the sine wave, right, or the cosine or the complex exponential, and that's the phase, and it has units of radians. Omega, so this is omega, not W. Okay, omega is the angular frequency, and it has units of radians per second. Beta is what we call the wave number, and it has units of radians per meter, or sometimes we would just say per meter. So just a little bit of terminology there. Now, since E, the wave, is a function of both z and t, space and time, it takes at least, well, it takes two figures to plot E. Right, so let me show you that. So we could take a plot of versus E versus Z, right, at one moment in time. So we'll just say one moment. So for a fixed t, one moment in t, right? And then we could plot what the sine wave looks like. So we pick our favorite value of t and plug it in here, maybe 0. And then we would make a plot of a sine of negative beta z. And depending, it depends on what value of t we chose, but it would look like this, something like this. Okay, a sine wave. That's not a very good sine wave that I've drawn there, but you get the idea. And the height of that thing is a. That's the amplitude. And the height down there is negative a, negative amplitude. And this is plotted versus z. And so when it starts to repeat, like right here, right, we call this distance, z is spatial, so it's got a distance of length, or meters. We call that length lambda, and that's the wavelength. And it certainly doesn't have to be from zero crossing to zero crossing. It could be from, its maximum to its maximum. That would still be lambda. Any feature to the next occurring feature. And so this, on the axis, that would be lambda, because this is 0 and this is lambda, and this is lambda over 2 then. That's half of the wavelength. And this is lambda over 4, a quarter of the wavelength, and this would be 3/4 of the wavelength. 3/4 lambda. So that gives us one picture, but remember, to fully understand what the wave is doing, we have to have two pictures. It's a function of space and time. Now, in this simple example, they're going to look very similar, but that won't always be the case. So now what I could do is plot one point in space. One point in space. Okay, and then plot versus time. So how does the electric field or whatever field change at that one point in space as I let time go by? And so now this horizontal axis has units of time, like seconds, and so I can take one feature like the maximum to the maximum, and we're going to call that capital T, and we're going to call that the period. And certainly I don't have to look at maximum to maximum. I can look at zero crossing, upward going zero crossing to upward going zero crossing. That is also the period. And so on the axis, that would be T right there. And then here's half the period, capital T over 2. Here's 1/4 of the period, capital T over 4. And here's 3/4 of the period, like that, 3/4 T. And just some more terminology. F is what we call the Hertz frequency, and it has units of Hertz, named after the scientist who discovered radio waves, and 1 hertz is like 1 cycle per second, and so there are these two ways of measuring frequency. Remember, we called omega the radiant frequency, and they're related like this. So 1f is 1 cycle per second. So if you multiply 2 pi radians per cycle times cycles per second, you have radians per second, and that's precisely omega. So, and then like we said, t is the period, right? So that is the number of seconds per cycle. So if you take the reciprocal of that thing, that would be cycles per second, and that's exactly the Hertz frequency. So they can be related like this. Okay, we talked about the wavelength, lambda. It has units of meters. Now, if you take the wavelength, or excuse me, if you take the wave speed, which is meters per second, and you multiply it by the amount of time it takes to repeat, so meters per second times seconds, then you get the amount of distance it takes to repeat, i.e. the wavelength. And then if you combine a few things, we said that the wave number was omega over u, the wave speed, and if you make a couple substitutions, you can get that the wave number is 2 pi radians over lambda, like that, the wavelength. Okay, so maybe you suspect something is coming here. We're talking about waves now. We've been talking, of course, about electromagnetics. What we've got coming up now is my favorite part of electromagnetics, light. So I will see you in the next video. Thank you.